Okay, cool. Please take it away.
Okay. All right. First of all, thank you very much, Stefan, for the invitation for this talk, and also for all the other guys from CERN that are involved in this Cyclops project. And so today we're going to cover the CARM tool, which is the tool to build the cache-aware roofline model for HPC, which is one of the research contributions of our research group at INESC-ID. I will be handling just the introductory slides, while afterwards Jose will be doing a complete set of the tool explanation, how we build it, and the complete demo, which is actually the outcome of his full effort during the thesis in our team and now continuing as a developer. So starting with the explanation of who we are and where we are. So we are coming from the INESC-ID, which is the public but privately owned institute for the research and development in Lisbon, in Portugal, which is closely related to the EST, which is one of the largest and the universities in Portugal, and especially in Lisbon. And within a specific group, like INESC-ID has many different areas that we cover research-wise. And the specific one that we belong is the High Performance Computing and Architecture System Research Group, or HPCS, which covers obviously a wide range of HPC topics, covering both the software, architecture, security, and really wide range of topics related to the HPC. If I have to, let's say, come up with one sentence to describe what we are actually dealing with, it's typically trying to tackle the challenges of modern applications and finding solutions to answer their computational demands, and trying to establish the methods to efficient use of HPC resources. And typically what we're tackling is the use of very different devices, starting from the CPUs, GPUs, Tensor cores or MPUs, or any other domain-specific accelerators, including the development of specialized architectures. And the one specific approach that we're going to cover today in the talk is by using the insightful performance modeling, or more directly cache-aware roofline model, in order to see how we can characterize the maximums of the computer architectures and see what is your exploration space when you want to optimize your application, and how much that architecture can actually give you performance-wise, and also how from that very simple insightful performance modeling we can derive certain optimization guidance in order to improve the performance of our applications in order to reach those maximums. So that would be, a very brief intro from our part. From this, I will handle it to Jose for the part of the tool, introduction, state of the art, and demo. Thank you very much.
All right. So starting with a little bit of motivation here. So as you may know, modern high-performance computing systems have been becoming increasingly complex and heterogeneous, and this results in them becoming harder to understand due to so many differences, implementations, and architectures. So this leads to an even harder time when you attempt to optimize applications for those systems. And so with this, we need an accurate but also easy to understand model that can facilitate application optimization for various systems. And this is the main appeal of the CARM model. It provides an easy to understand and accurate performance overview of your system, along with some good optimization hints for profiled applications. However, currently the CARM model is only supported by Intel Advisor, which limits its potential users. So this problem is the main objective of the CARM tool, to port the CARM model to other CPU vendors in an open source format, specifically AMD, ARM, and RISC-V CPUs, alongside the support for application analysis in the scope of the CARM model, and finally combining all of these functions inside the single tool, which is the CARM tool. So this is actually a complicated process, because in order to build a CARM model for a CPU, you will need some tailored micro benchmarks that can take full use of the CPU memory system and floating point units. And this requires having a good understanding of the different underlying architectures and the ways to maximize their utilization. So at the end of this talk, I'll also show you some experimental results obtained with the CARM tool, such as a CARM-based architecture and application analysis. So these are the contents of this presentation. We'll start with the state of the art, then present the CARM tool, and then move on to the experimental results and the conclusion. So in this state of the art overview, we'll give you some context around modern CPU architectures, the cache-aware roofline model itself, other tools that also implement the Roofline model, and application analysis tools based on performance counters and dynamic binary instrumentation. So starting with a quick look at the general modern CPU architecture that vendors such as Intel, AMD, ARM, and RISC-V implement, these architectures usually contain multiple cores which work together to execute various instructions. And when it comes to instructions themselves, we have a big variety of different units inside each core responsible for the different instruction types, such as integer and floating point ALUs and memory units. And usually these CPUs also have a memory hierarchy based in multiple levels, with different sizes and bandwidth that can sometimes be shared between cores. And besides the memory, the computational capacity of the cores can also vary greatly between vendors, and this is part due to details like vector extensions that an architecture implements. So in this case, each vendor utilizes their own vector extensions, where Intel and AMD both use SAC, AVX2, and AVX512, while ARM uses Neon and more recently SVE, and RISC-V implements RVV. So these extensions must be fully utilized in order to extract the peak performance of a CPU, which is crucial for the car model. And for this reason, each vector extension will need its own tailored micro benchmarks in order to properly evaluate the performance of a CPU in the context of the car model. So now talking about the CARM itself, so how does it actually work? The CARM has two main roofs, the sloped roofs in red, which are based in the maximum bandwidth of the different memory levels of an architecture, and the flat roof in blue, which is based on the peak floating point performance of the architecture. And these roofs designate two main areas of the CARM model below them. These are the memory bound area in red and the compute bound area in blue. So if your profiled application ends up in the memory bound area, like the first point in the graph, the CARM indicates that we should first try some memory-related optimizations in order to see the best performance gains. While if we fall on the compute bound area, we should first try to improve the utilization of the arithmetic units of the CPU, for example, via vectorization of floating point operations when possible. And finally, if we are in the mixed area, then both strategies should be considered. However, like I said before, to build the CARM properly, you must utilize microbenchmarks to get the realistic sense of the maximum performance of the CPU, instead of relying on possibly unachievable theoretical values reported by the vendors. And this is done via memory microbenchmarks to determine the maximum bandwidth of each memory level, and floating point microbenchmarks to determine the peak computational performance of the CPU. So the main objective of the CARM tool is to automate this process via the automatic generation, execution, and measurement of these assembly level microbenchmarks that can fully use the target system to build a CARM model on any platform. So, like I said before, the CARM is officially supported by Intel Advisor. However, there are other tools that also implement the concept of Roofline model. So, for example, AMD UProf and DRT, the empirical Roofline toolkit, starting with Intel Advisor, which also includes the possibility for application analysis in the context of the CARM via dynamic binary instrumentation, while AMD UProf does something similar via performance counters. However, AMD UProf only implements the original Roofline model based in theoretical values. And then, besides these two closed source tools, there is ERT, which supports CPUs from both vendors. However, it does not explicitly state which type of Roofline model it implements, but it produces something very similar to the CARM. However, DRT does not provide any way to analyze applications in the context of the CARM, and as you may have noticed, none of these tools are able to provide support for other vendors like ARM and RISC-V, which is exactly the problem that the CARM tool attempts to fix via the support for these vendors, and by also providing both DBI and performance counter application analysis options for even more flexibility in its utilization. So to provide this performance counter-based application analysis support in the CARM tool, we looked at various performance tools that we could integrate to achieve this functionality. So we tested 4 main tools, which were PAPI, Perf, Liquid, and Performance Copilot, or PCP, which are all open source. However, for the sake of time, I'm only going to discuss PAPI and Perf, since PAPI is currently the performance counter tool, which is integrated with the CARM tool, and we plan to add Perf support soon too. So PAPI has the advantage of being able to abstract the details of the performance counters of each vendor and provide a consistent interface, which facilitates the analysis of applications in various architectures, having only the main disadvantage of only allowing for region of interest profiling in an application, when sometimes it's also useful to profile the entire execution. Then we have the Perf tool, which is part of the Linux kernel And this tool is the one with the support for the most architectures, since it's basically supports any architecture supported by Linux. However, its interfacing is not as easy to port across different architecture, which is why its integration is still a work in progress. So besides performance counters, other strategies can also be used for application analysis, such as dynamic binary instrumentation, which has the advantage of not needing any root privileges to be utilized, and which can be a requirement in certain systems when it comes to performance counter access. And for this reason, we implement both Intel SDE and Dynamo Rio as options for DBI analysis in the current tool. So starting with Intel SDE, which allows us to analyze a list of all the executed instructions by an application, which are then used to calculate the performance metrics used by the CARM, such as arithmetic intensity and gigaflops, which are necessary to plot an application in the CARM. However, Intel SDE is closed source, so this does not allow for much customization besides what is already offered. But since the tool already provides enough information for analysis, it is currently supported. So another limitation of Intel SDE is that it's limited to Intel and AMD, while open source tools like Dynamo Rio can also support ARM and more recently RISC-V, although still in initial stages. This tool only takes slightly longer to perform application analysis. However, it allows for the extension of support for application analysis to ARM and RISC-V system. So since this tool is open source, it was integrated with the CARM tool via custom Dynamo Rio client. So now moving on to the next section, where I'll present the CARM tool itself. And I'll also switch from the slides sometimes to show different features of the tool live. So here I'll give you an overview of the CARM tool, starting with a high-level view of its functionalities, like the graphical user interface, automatic benchmarking, and application analysis. And then with more detail on some important parts, like the benchmark generation, frequency measuring, and the benchmarking itself. So starting with the high-level view, the CARM tool can be described through its various independent modules, which implements each of its main functions. So to use the tool, you can use both the command line or the graphical user interface, from which you can start up the necessary benchmarks to obtain the CARM for your system. And you can also perform the application analysis via performance counters or dynamic binary instrumentation. So currently the CARM tool supports most vector extensions of the main CPU vendors, with the exception of ARM-SVE, which is a work in progress. And with this, I mean that the CARM tool is capable of generating the assembly micro benchmarks that can make use of these vector extensions when they are available in the underlying system. So these high-level modules are implemented by the various files present in the source code of the CARM tool, and I'm now going to give you a brief overview of what each of these modules does. So starting with the graphical user interface, this interface runs on your browser using the Dash framework, which, as you can see, can be used for result visualization of both CARM and application analysis. Besides that, you can also launch the CARM benchmarks directly from the GUI using the sidebar. And finally, you can also start application analysis in the interface itself. And now for a quick demo of this, I'll start up the interface here in another tab and show you. So to start up the interface, you just need to run this simple Python script. So this will give you a link that you can then open in your browser, which I have over here. And so from here, as you can see, you can run your CARM benchmarks. From the sidebar, you can configure the different settings you want, like thread counts, the ISA to benchmark, the precision, among other things. And you can also just run it with the default options. So this will give you some intermediary output, which you can consult in the terminal. And this includes things like the detected ISA extensions, the size of your caches, and the tests that it will be performing. So in this case, by default, we test all of the available ISAs with double precision on one thread. And then you can also consult the intermediary output of the benchmarks here when they are finished. But for now, I will just stop them because they will take too long to wait for now. So you can do this by clicking here on the Stop Benchmark Analysis button. So then you can also run your application analysis via this form where you can input your machine name and then select it from the different options like DBI, region of interest DBI, or performance counters. Then you just need to provide a file path to your executable and some arguments that it might take. So in this case, I will actually leave running one application that I have here. And for this, I'll just fetch the path to the executable and the arguments. So this is a simple SPMV application that uses the Huygens library, and it takes as an input a matrix, as you can see, and then just a number of iterations for it. So with this, we can click Run Application, and then we also get some intermediary output here, which we'll see later. So you can also then check your results here. So this will fetch from the available results you already have in your machine. So in this case, from my laptop here, you can then select from whatever is stored. So in this case, I have a lot of different results here. And then you can also compare two car models of different settings to see how this changes the peak performance of your CPU. And you can also plot your applications from the resulting application analysis, as you can see as dots that will show up over here. For example, over here and here. So this is a brief overview of what you can do with the graphical user interface. So now going back to the slides and moving on to the automatic benchmarking. So first, to facilitate its utilization, the CARM tool automatically detects the more important aspects of the underlying system, like you saw just now, such as cache sizes, availabilizers, or even the maximum supported RVD vector length in a RISC-V system. And this is all done by the files in the config folder. However, you can also manually provide these details. And these details are then used to generate the different necessary benchmarks to build a CARM model. As you can see in this GIF, some examples of those various micro benchmarks for different ISA extensions. And these are automatically generated and executed thanks to these two modules, bench and test, which I'll talk more about later. So finally, I will also give you an overview of how the application analysis is implemented. So this was done via the integration with other performance tools, such as PAPI, DynamoRio, and Intel SDE. So starting with PAPI, this allows us to access the performance counters of the system, and we take advantage of the high-level API from PAPI, which allows us to define a region of code to be analyzed, from which we extract the necessary performance events to plot an application in the CARM. And for the dynamic binary instrumentation, we use Intel SDE and DynamoRio, and we also developed a way to automatically interface with them and define region of interest from which we obtain a breakdown of executed opcodes, which is then used to calculate the CARM metrics like gigaflops and AI to plot the application in the CARM. And this last integration is facilitated by the DBI CARM ROI header file, which contains a simple API we developed to interface with both DynamoRio and Intel SDE to define the region of interest. So now I'm also going to quickly show you how you would do this yourself. So here is the source code for that SPMV application I left running before. And as you can see, all you need to do is include the header files necessary for the DBI region of interest definition or for the performance counter, the PAPI header file. And then you can go ahead and just use the API functions to start up your region of interest. So these are the CARM ROI begin for the DBI and the PAPI high-level region begin for the performance counters. And then you also use the equivalent ones for the end of your region of interests. And so let's see if our application is finished. So we can see here from the terminal some of the intermediate outputs. So we get some results in the form of the total floating point operations, memory bytes, execution time, gigaflops, bandwidth, arithmetic intensity. And in the case of DBI, we also get a breakdown of the different opcodes that were detected during the execution of the application. And now, if we head to the GUI and we refresh this page, we should now be able to see our results here. So I'll just plot those now. So here we have it from today, this one, which was using DynamoRio region of interest, as you can see here. And once this updates, we'll see the results. So as we can see from an SPMV application, this is to be expected. We are very memory bound, as indicated by the CARM model. And what I will actually do is also showcase a small improvement that you can do to this particular SPMV implementation, which is by using an RCM matrix instead of the original matrix, which this reordering actually makes better use of the caches, improving our memory performance, which should also boost our overall performance. And so for this, I will actually just start up another analysis. So again, this is the name I have for my laptop here. I go DBI Roy, and now with the same executable, just changing the name of the matrix. So here it's called the same thing, but with RCM. And now I'm going to have this run. And in this case, we'll wait for it to finish because it should be quite fast. So as you can see now, it's running it first for timing data, which in this case finished. We get here theoretical gigaflop 0.21. And then we also get now the opcode breakdown here, which gives us our results again. And we got 0.21 gigaflops here. So now let's check by refreshing this if it shows up over here. And in this case, I'm also showing the scalar and the one thread results because this application is currently running with just one thread. And we can already see here that we have 0.21 gigaflops instead of 0.12. So we should expect the point here now to be, slightly above. This is a log scale, but our arithmetic intensity does not change since I did not change the code itself. Just the way we are using the caches has resulted in some more gigaflops. And now I'll go back to the slides. So now I'll talk. It's like it froze. Okay, so now I'll talk in more detail about what was done to allow for the support of different ISA extensions in the CARM tool, which start with the automatic generation of micro benchmarks that follow a similar general structure for all the vendors, which is then adapted to the limitations of each ISA. And this is followed by a frequency measuring step, and then some preliminary timing tests to ensure stable results, and finally the benchmark execution itself. So all of these steps are implemented by the various files you see here, starting with the benchmark generation in the blue module. So the benchmark generation module is implemented by these various C files, which have as a final product the various benchmarks you see here. So these files actually store the different assembly instructions and registers used by each ISA that we support, and automatically perform the necessary calculations to generate the assembly code that respects the specifications of the user. So most benchmarks will have an inner and outer loop, as you can see in this GIF, in which the inner loop contains a fixed number of iterations to ensure we perform the specified number of instructions, while the outer loop can be adjusted externally, which allows us to vary the execution time of the benchmarks. And I will quickly show you this in action by starting up some different benchmarks so we can see how they change. So here in this file is where we store the assembly micro benchmark that will be executed. And in this case, I have here some different commands that will start up different benchmarks. So this is also how you would use the tool in the command line. You would simply call the run.py script. Then the v flag is for the verbose to get more intermediary output. Then you just need to select your instruction, your ISA and type of test, and you are good to go. So for example, if I start up this scalar L3 benchmark, we can see that our assembly now changed to be using some scalar memory operations. And then, for example, if we switch to an AVX2 floating point benchmark using FMA, we now get those instructions in the assembly. And finally, you can also mix both types of benchmarks via the mixed benchmarks, and you can have floating point and memory at the same time, in this case for the SSE vector extension. So this does not require any knowledge of assembly. You just need to select what type of test you want to do and select the ISA, and you are good to go. And you can even specify your own ISA via this header file that we have here, which is how we store all of the different register names, instructions, among other things necessary to generate this assembly. So as you can see, we have some here for different ISAs. And although this is not fully automated yet, we are working on having it be very convenient to add new ISAs very quickly. And so with this, we now move on to the frequency measuring part. So to do the frequency measuring, we use an assembly function that performs a series of dependent additions. And these lead to only one instruction being performed per cycle by the CPU. And then by knowing the number of instructions performed and the time taken, we can obtain the frequency of the CPU. And this method has been used in all tested machines and show deviations under 1% from expected values. And then to measure the time taken by the execution of this function, we use the timestamp counter in Intel and AMD CPUs. And for ARM and RISC-V, we use the clock@time function. And so now to finish, after generating the benchmarks and measuring the CPU frequency, we are now ready to start executing them. And so all of this happens in the main test.c file, which coordinates the creation of threads, memory allocation, frequency measuring, and benchmarking. And as I mentioned before, the CARM tool first runs the benchmarks to determine how long they will take, to then adjust their execution time via the outer loop to ensure they last enough time to produce stable results, but also don't take unnecessarily long times. So finally, then the tool executes these benchmarks 1,024 times, and then the best run is selected, from which the bandwidth and peak gigaflops values are calculated. And so now I will talk about some experimental results that were obtained when using the CARM tool. So this includes a CARM-based architecture analysis of different vendors, a comparison with Intel Advisor and DRT, and the analysis of an SPMV application using the CARM tool. So starting with the machines that were used to obtain these results, we have one from each vendor. So these are the Venus machine with a Skylake X CPU that implements the SSE AVX2 and AVX512 extensions, the Kata machine with an AMD Zen 3 CPU which implements SSE and AVX2, ARM-Q with the Vulkan architecture that has the Neon extension, and the Milk5 machine, which is a RISC-V system with RVD 0.7.1. So besides that, the CPUs of all machines have 2 floating point units per core, and between 3 and 1 load store units per core, which are used to define the theoretical limits of each architecture, which will now be analyzed. So starting with the memory system of each CPU, for that I will use these bandwidth graphs, which show the measured bandwidth and instructions per cycle and how they change as we increase the amount of memory used in our tests. So this graph is also generated by the CARM tool and uses the same benchmark used for the CARM generation. So in the Venus machine, which is the one we see here, we can see that we stayed slightly above 2 instructions per cycle. And this is actually considerably lower than the expected 3 instructions per cycle that the 3 load store units should be able to support in this architecture. However, this limitation is also reported by Intel, which in their hardware optimization manual also specify that the Skylake X architecture is only capable of sustaining around 2 memory instructions per cycle, which matches our results. Then in the Kara machine, we can reach the expected 3 instructions per cycle with the load store ratio that best matches the 2 load and 1 store units of the Zen 3 architecture. And we can even confirm the presence of this exact number of units, since in the load-only test, we only reach 2 instructions per cycle, while in the store-only test, we only reach 1 instruction per cycle. Then in the ARM-Q machine, we also reach the expected limit of 2 instructions per cycle, and we can also see that only one of the units is capable of performing stores, since we only reach 1 instruction per cycle in the store-only tests. Finally, in Milk5, we reach the expected 1 instruction per cycle, while in the store-only tests, we can observe some unusual behavior here, where we maintain 0.5 instructions per cycle until about 16,000 kilobytes. And this is likely due to the adaptive write allocate policy of the CPU, which actually deactivates the write allocate when multiple stores are detected in series, which then bypasses the cache levels, which is why we don't see the same performance degradation as we move through the different sizes. So to sum it all up, in this table, we can see that it was easier to achieve the expected values in the memory levels closer to the CPU. And in the case of the ARM-Q and Milk5, there were no realistic theoretical data with which to compare. Since that, for example, the cited theoretical L2 maximum bandwidth of the ARM-Q CPU should allow for 4 instructions per cycle, which is already twice as much as the load store units in this architecture. So now, moving to the analysis of the computational capabilities of each machine, for this we can use the CARM itself for each system, which defines in its flat roof the peak gigaflops obtained during benchmarking, where I also added the corresponding instructions per cycle measure to compare with the theoretical limits. And we can also check the performance obtained from mixed benchmarks that perform both floating point and memory instructions at the same time to see if we can stay close to the performance roofs of the car, which are these various dots you see here in the plot. So starting with the Venus machine, which nearly obtained the 2 instructions per cycle expected for both AVX512 and Scalar, but then the mixed benchmarks also stayed relatively near the car roofs, except for the FMA AVX512 ones with 25% deviation. Then in the car machine, we accurately reached those 2 instructions per cycle with AVX2 and Scalar, while the mixed benchmark also remained relatively close, especially for the add instruction, with only around 1% deviation in both AVX2 and Scalar. And then on ARMQ, we again reached those 2 instructions per cycle, but the mixed benchmark did not perform as well, with the Scalar ones having around 17% deviation and the Neon benchmarks with around 25%. Then finally on Milk 5, we can again obtain the 2 instructions per cycle on the floating point side, but then we get also some smaller deviation from the mixed benchmark compared to ARMQ, with at most 10% deviation when using RVV. So basically the floating point limits were generally easier to achieve in all architectures, as you can see from this table that sums up the deviations. However, the mixed benchmarks show that by stressing the memory and computation at the same time, pipeline conflicts can lead to some slowdowns, particularly when more complex floating point operations such as the fuse multiply add are used. So we also compared the results of the CARM tool with other Roofline tools in the Venus machine, and in this case, ERT and Intel Advisor, to determine if the values we obtain can also be reached by other tools. And in this case, starting with the AVX512 results from the ERT tool, from which we obtained some similar values for the floating point roofs, but lower bandwidth measurement for the L1. As you can see from the red lines here, that correspond to the ERT results. But then for the other memory levels, ERT managed to obtain some slightly better values, which can actually be explained by the way ERT actually determines the different cache sizes in a system. So this is actually based on bandwidth measurement variations between different bandwidth tests. So this means that if the tool finds a big enough variation in bandwidth between tests, it will assume that it is now testing a different cache level. And this method can result in wrong assumptions about the cache sizes. And sometimes the tool can even report more cache levels than what is present in the system, which makes it possible that the measurements from a slower memory level could easily be affected by the measurements of a faster adjacent level, which leads to these higher results. So we also compared with the AVX512 results of the CARM tool. We also compared the AVX512 results of Intel Advisor with the CARM tool on the Venus machine. So here we managed to obtain similar values for the floating point and L1 roofs, around 222 gigaflops for single precision FMA and 479 gigabytes per second for the L1. However, Intel Advisor also managed to obtain some considerably higher values for the L2 and DRAM. But this is also mostly due to the fact that Intel Advisor adapts its load store ratio to each memory level to get the best possible results, while the CARM tool employs the same load store ratio across all tests for consistency. So, for example, by running the L2 tests with a load-only configuration, we can actually get around 221 gigabytes per second. And for the DRAM, we can also obtain almost 20 gigabytes per second. And with this, we managed to surpass the values obtained by Intel Advisor. And now, finally, to demonstrate the application analysis functionality of the CARM tool, we analyzed an SPMV implementation using the Huygens library in the Venus and ARMQ machines to compare the difference in the implementation of SPMV by the Huygens library in different architectures. So besides that, we also tested the impact of using an RCM reordered matrix in the performance of SPMV execution, like I showed you now on my laptop. And first off, as you can see, the Venus machine obtained more gigaflops than ARMQ, which is expected due to its superior CPU, which can also be seen by the higher CARM roofs in black that belong to the Venus machine versus the ones in red from the ARMQ machine. So besides this, we can also see a discrepancy in the arithmetic intensity of both machines, which indicates that the Huygens library might implement SPMV differently in ARM and Intel architectures. And so now looking at the performance difference between the original matrix in blue and the RCM matrix in green, we can see that the RCM reordering almost doubled the gigaflop performance of the SPMV execution. And besides that, in the ARM-Q machine, while we only performed the DVI analysis, since we did not have the necessary permissions to access performance counters, however, this analysis was done in the Venus machine, which corresponds to the dots outlined in red, while the DVI analysis corresponds to dots outlined in black. And here we can see that both analysis methods, despite being quite different in their approaches, managed to obtain quite similar results with only some slight discrepancies. And so now we have reached the conclusion. But before that, I'll just give you a quick showcase of how the different ISA extensions and memory levels used can actually affect the peak performance of your system. And for this, I have some results from mixed benchmarks using the different ISAs and targeting different memory levels to show you. So first off, starting with a DRAM benchmark using the scalar, the scalar instructions. Here we can see from this dot that since our arithmetic intensity is already not being affected by the roofs of the DRAM, we reach the peak performance possible for the add instruction in this system. So in case this was your application, for example, you would have to improve your performance, you'd have to look into using some vectorization. In this case, I have the same DRAM benchmark, but now targeting the ADX2 instruction set, which should now provide us with some more performance. And as you can see, those results ended up over here being limited by the roof of the DRAM level for the AVX2 ISA. And in this case, now what you need to do is try to improve your utilization of the caches. And to exemplify this, I also have results of the same benchmark using AVX2, but now targeting your L1 cache. And from this, we can see that we can end up here in the add roof of the AVX2 performance. So the only way now to get better than this would be to look into using FMA instructions in your application if possible, which is what I have here as the final dot that will show up. And as you may know, FMA instructions actually perform 2 floating point operations per instructions, which is why we get double arithmetic intensity. Since I kept the ratio of memory to floating point instructions the same here, but then FMA does twice the number of flops, so we get twice the arithmetic intensity. So this is kind of how you would use the different roofs to guide your optimization efforts. And so now, in the conclusion, I'll just briefly talk about some ongoing collaborations to integrate the CARM tool in various European projects and organizations, such as POP3, Cyclops, CERN, and VSC, alongside some completed collaborations, such as with the Sparsity project, which resulted in the development of the live CARM in the SuperTwin tool. And finally, I'll mention the CARM tool GitHub and its paper. So starting with the ongoing collaborations, the CARM tool is undergoing developments to be integrated with other application analysis tools, such as Adaptive Curve from CERN and Paraver from VSC, to provide support for application analysis in the context of the CARM in these tools. And besides this, collaborations with POP3 and Cyclops are also undergoing to analyze applications developed in these projects, such as a SQL-based database being developed in the Cyclops project, with the objective of finding ways to improve performance. So now moving to complete collaborations, such as the live CARM dashboard developed in the SuperTwin tool. So this feature was developed by including the CARM tool source code directly in the SuperTwin tool, which then automatically interfaces with the CARM tool to realize the necessary benchmarks. And then these are combined with the live performance counter data from SuperTwin, which allows for the analysis of applications during their execution. So the live CARM can then be used, for example, to compare different SPMV algorithms, as you can see on the image on the left. And you can also do some validation of micro benchmarks from other tools, such as Liquid, in which we also verified that the CARM roofs imposed by the CARM tool were reached by the other tools, but without being surpassed. And so the CARM tool is open source and available on GitHub. And we also have an accepted paper about the tool, which will soon be published in IISWC 24. And the CARM tool is the first of hopefully many tools to be developed in the scope of ChampHub, which is the heterogeneous computing and performance modeling hub created by INESC-ID. And so with this, I conclude my presentation. So if you have any questions, feel free to ask.
Thank you very much, Jose. Very nice presentation.
Thank you.
Any questions?
just to start people off, just the obvious question: the slides you will allow us to upload the slides later on, right?
Yes.
Because all of the links and things will be nice to have.
Sure thing.
Okay. So,
please, there was a question from
Adrian.
Adrian,
okay.
Please go ahead.
So this is a bit of a silly question, but do you have plans to improve the performance of your GUI, which seemed very laggy on the demonstration that you made?
So this usually doesn't happen. So for some reason today my laptop is acting up. It's actually doing a lot of fan noise, but since I'm using a different mic, you don't catch it. Usually when I present this, it's not as laggy, and usually there's not such an issue, with the time it's taking to generate. But I do have an idea of some optimizations that I can do to possibly improve this. Yeah. So yeah, it might be an issue on some slower machines maybe. So I will consider that.
Okay.
Attila, please.
Well, I have a very naive question. So the big question that I always have with these sort of relatively low-level profiling tools is how to apply them to a relatively large code base. So do I understand correctly that in order to try to use this sort of profiling, either you should already have a good understanding of what part of the code you want to optimize, or on one of the final slides, I thought that was a pretty useful thing, because this is what I wanted to ask about. So do I understand that the other possibility for using the tool is, well, you just continuously measure the what the hell? Okay. Oh,
something went wrong.
Yes. So that the other option is that you just monitor what happens with your code on every commit, sort of, and try to understand, what helped the code, what didn't help the code.
So I actually lost you for a second there. I don't know if you noticed in my screen share, because my computer, like I said, is acting up today, and I missed the previous 20 seconds.
Okay, so the short version of my question, generally, how is one supposed to use this sort of profiling on a large code base? So what's the recommendation?
So in that case, for now, we only focus on, you provide your executable, and you can either profile the entire execution of this executable via DBI, or if you have the knowledge of the areas that you want to look for in your application, you could perform the region of interest analysis. So right now, we don't have a very good, we don't have more options other than these ones, which might limit what you can do for very large code bases, especially if you don't know where to start. Currently we don't have a very good way. However, we also want to, through our collaborations with other tools, for example, Adaptive Perf, get the performance analysis from Adaptive Perf, which can actually produce to you a heat graph that will point to different parts of your code, that will allow you to pinpoint different sections that might be causing the slowdowns. So in the base tool, no, not right now, but in the future, through our integrations, it could be an option.
Do I understand correctly that the idea is to do PMU analysis, where for each PMU sample you use instruction pointers to find which symbol the activity happened in, and then discriminate your roofline points by application symbol?
Yeah, so that's basically what we plan to have via our integration with the adaptive perf tool. Because right now, you just use the high-level API from PAPI, you define your region of interest, and then after compilation and running via the CARM tool, you just get the cumulative report of that section of the code. But then with the adaptive perf tool, we could have something more like that.
Okay, thanks.
Just one question from my side.
Yes.
The you were talking about vector instructions quite a lot.
Yes.
Is it? I mean, we are now looking a lot in our code into utilizing vector instructions. On the roofs that you are plotting, the possible peak performances, would it be possible to show a roof for scalar and the vector, or?
Yeah. For example, it's what I have here. So in red, you can see the results of the scalar benchmarking, and then
perfect.
in black, AVX2, for example.
Yeah.
And you can compare them.
Thanks.
So just as a very cheap comment here, the labeling on these plots might be improved a little bit, because most of the time you know from context which set of lines belongs to which instruction set, but still.
So basically that part kind of comes from the labeling itself, kind of ends up coming from the drop down of your selection. And so the first results correspond to the black, and the second ones always correspond to the ones in red. But we do need to improve this, because for now I just show the labeling for each line, but not the corresponding ISA and settings. And this is actually because there are a lot of settings that you can change around, and at the time it resulted in some very long labels. So that's why I kept it this way for now. But that's definitely something to see. Maybe how I could do this better.
You could take some inspiration from the plots that you showed in your presentation, where you had some inset that gave some detail of which machine you're talking about.
So the ones from the presentation, that would be an ideal version, for example.
I mean, possibly, but in this very specific plot, you always have a maximum of 2 CARM results. As long as you just color the top 2 rows, or just put some label there that this is black, the next one is red. Yeah, that would already help.
Yeah, I will probably do that then.
Great, thanks. I missed that. Okay, thanks. Any more questions to Jose or to Aleksandar? Yes, please go ahead.
Okay, my question is about precision. So if you can specify precision there, then then what exactly do you profile? Because in the code usually you have different precisions mixed.
Single and double.
So but if the kernel contains.
Sorry. So currently for the benchmarks themselves, you can either select double precision or single precision. However, in the side of application analysis, we also do check how much of your percentage of instructions are coming from double precision and single precision, for example, in the PMU analysis. So as you can see here, maybe it's not very readable, from the name of the kernel of the analyzed application, we also give some details, for example, here AVX2, double precision. So these kinds of things are detected when possible from during the execution of the application, during the profiling. But then in case you do have a mix, like 50-50 or something, we then attribute the mixed label instead of single precision or double precision. However, right now for the CARM benchmarks themselves, we don't have a way of mixing single precision with double precision. However, it could be implemented, this functionality.
Yes, yeah, that was my question. Yeah, thank you.
Maybe two small questions. One, I saw that currently you do not have an option for PMU analysis on uninstrumented binaries. Do I understand correctly that you plan to eventually do this via perf?
Yes, that's the plan.
Okay. And second question, are you able to deal with programs that spawn subprocesses?
So right now with the PAPI interface we have observed that it can detect subprocess and it can follow along, when you spawn different threads and detect them. And we also number that from the results. So if you run an application with multiple threads, we will check how many threads. PAPI can actually check how many threads you are using. And then on the DBI side, when you have multiple threading, it works. But I don't think we have thoroughly tested the part of subprocesses in DBI.
Yeah, because things like Python may make this an issue. So.
Yeah.
Thank you.
Okay. Any more questions from remote?
It looks like Max added something here, and he's actually the one working on adaptive perf. So he says that adaptive perf should soon be able to call the CARM tool automatically, use the benchmarking information produced by it to render similar roofline plots that you see here in this GUI within adaptive perf profiling, and then it will give you some points of user selected code regions. So it was basically what I was talking about, that through our collaborations, in this case with adaptive perf, we plan to refine the profiling side of things, basically.
Okay, yeah, and maybe just to refer, Max has presented adaptive perf in a previous Compute Accelerator Forum, so you can go back to the slides and the recording from there if you like. Okay, I don't see any more questions. Last chance to ask. No? Okay, thanks a lot then. Thank you very much, Aleksandar and Jose. And yeah, and we'll upload the slides and the recording to the Indico page and the YouTube channel, and talk to you in October then. Okay, thanks everyone. Bye-bye.
Thank you. Bye-bye.
Thank you.